Hi, this is video 3 of 3 for the respiratory system responses, section A. So we need to look at how to read the dissociation curve. We need to look at why the curve moves and how the curve moves and what the movement means in terms of oxygen dissociation. To understand that, we've got to look at saturation of hemoglobin, diffusion gradient and concentration and partial pressure. This red blood cell has hemoglobin on and it has 2 oxygen molecules. The 2 oxygen molecules are only half of what the red blood cell or hemoglobin can carry, so it is said to be 50% saturated. This red blood cell has 4 oxygen molecules on it, so it's 100% saturated. No more oxygen can go onto the hemoglobin. Hemoglobin is a protein that is within the red blood cell. Affinity means to like, to enjoy being with. And we say that hemoglobin has a high affinity for oxygen. Saturation refers to the amount of oxygen that's attached to the hemoglobin in the red blood cell. 4 molecules is what we call 100% saturated, where no more oxygen can combine. When the oxygen is combined with a hemoglobin, whether it be 1 molecule or all 4, we call it oxyhemoglobin. That means that the hemoglobin or the red blood cell is oxygenated. Affinity means the degree one substance combines with the other, so how much they like to be together. And oxygen has a high affinity to hemoglobin in the red blood cells, and that's one of the reasons why it will move across from the alveoli, so the lungs, to the capillary, where it will find the hemoglobin. It's attracted to it. This is a little picture of the alveoli, the little cauliflower in the middle, and it shows the blood flow going round the alveoli. So it comes in through the blue side, and carbon dioxide that's produced in the muscles is moved across the 1 cell thick membranes of the capillary in the alveoli into the alveoli, and at the same time oxygen is being absorbed through its affinity, its like, its enjoyment, its love for hemoglobin, and diffuses across. So this happens at the same time, but you end up with oxygenated blood or oxyhemoglobin. Another reason why oxygen will move from one place to another is because of pressure or the diffusion gradient. Now these are 2 concepts that we will go on to explore here. So if the circles represent oxygen, that they are red blood cells, but let's say for the sake of partial pressure that they show a gas, we're looking at where gas would flow to. And here it shows on the right hand side that we've got 7 molecules of gas, and on the left hand side 2 molecules of gas. And what would happen is molecules of gas would move across the membrane if it was 1 cell thick, move across the membrane until it was equal on both sides. That's what we call equilibrium. So that's when it would stop. Now quite often we'll have 2 gases. Now in this case the blue gas represents carbon dioxide, and the red side represents oxygen. So what would happen across this 1 cell thick membrane? Well, the gases would move until equilibrium was reached. Now putting this into perspective, when you have worked out or done some exercise, your blood returning back to the lungs will be blue. It will contain a high level of carbon dioxide and a very low level of oxygen, which is represented on the left side of the screen. After it's been to the alveoli and the lungs, you will see more oxygenated blood, therefore red, and less carbon dioxide. When you get to the muscles, the oxygen will diffuse across into the muscle cell, and that capillary will now collect carbon dioxide from the muscle cell, so it will change, the partial pressures will change there as well. So partial pressure is the amount of pressure or force one gas exerts on another. So in this picture, which has the higher partial pressure? Well, it's the red slightly because there's more of them. And if there's more of one gas, then it exerts a higher partial pressure than the other one. But essentially, it's how dominant that gas is within all of the other gases in that area. So it's not talking about anything other than gas. So just to recap, before we talked about pH of the blood during exercise and the fact that the pH goes down. pH reduces to make things more acidic, and that is caused by carbon dioxide and by hydrogen that we get from lactic acid breaking down in the muscles. What happens to the temperature of the blood during exercise? Well, the temperature goes up. That friction in the muscles causes heat. Energy being produced within the muscle cell, ATP, that produces heat. The blood picks that heat up as well, and it's transferred around the body. Why do these things occur? Due to exercise, one session of exercise. Effects of the changes on oxygen's affinity for hemoglobin. This is key to understanding the next part. A reduction in pH, so increased carbon dioxide in the blood, and that is produced by the Russell cell, and that diffuses because of the diffusion gradient across the membrane of the muscle cell and the capillary. So increased carbon dioxide in the blood reduces the pH. If you're working particularly hard and produce lactic acid, which we all associate with that burning sensation, it means that lactic acid has been removed from the muscle cell and pushed into the bloodstream. It doesn't stay in the bloodstream as lactic acid, and we don't need to know the ins and outs of this, but what you do need to know is it forms hydrogen ions. So some of lactic acid in the blood breaks down immediately, and we've got hydrogen ions, and they are a problem to us. It's that hydrogen ion that also reduces the pH. So now we've got carbon dioxide in the blood and we've got hydrogen ions in the blood, both of which are reducing the pH. This reduction in pH is picked up by the chemoreceptors, and therefore our heart rate, or in response, our heart rate will increase and our breathing rate will increase because it's telling the body it's producing more carbon dioxide, it's working harder, we need to give them more oxygen. But what does this reduction in pH do, and temperature, do to reduce oxygen's affinity for hemoglobin? Well, it means that when the pH reduces and the temperature increases, it means that oxygen likes hemoglobin just a little bit less. Now, it will pass across at the alveoli membrane because of the diffusion gradients, because you've got no oxygen in the blood and you've got lots of oxygen in the lungs, and so the oxygen will go across because it wants to make that equilibrium state. It will move from an area of high pressure or concentration to low pressure and concentration. That will always happen. But the muscle cell now, it's different. So the muscle cell requires oxygen, but now, because of the pH, the change in the blood, the oxygen is more likely to leave the hemoglobin and go over to the muscle cell. It happens quicker, it happens faster. But that's amazing for sport, because it now means we're more efficient at getting oxygen into the muscle cell quickly for more oxygen. So this is great news for us. So what happens is oxygen's affinity for hemoglobin reduces. The impact of these changes is that oxygen will pass to the working muscle more readily than during rest periods, thus making oxygen delivery more efficient. I need to check my PowerPoints, don't I? So here's the oxygen dissociation curve. So we're going to have a read of it first of all. Now, what we're going to read are at two sites. We're going to read at the partial pressure of 40, and we're going to read at the partial pressure of 100. And the reason we're doing those, and it's the only two we're interested in, is because somebody's already researched it for us, and they have stated and said to us, at the muscle cells, the partial pressure of oxygen is always 40. So we also know that the partial pressure of oxygen at the lungs is always 100. Now we record this unit, the partial pressure, in millimetres of mercury, written mmHg. So let's read the graph at 40 first of all, where we know we're at the muscle cells. So we're looking at how saturated the red blood cells are when they're at the working muscles. So let's read up to the black line and then read across from the black line, and that will give us our percentage. So you can see we're around 70% there. Now let's read 100 millimetres of mercury, the pressure at the alveoli. We go up and we're near to 100% saturation. So what that tells me already is that at the working muscles, sorry, not at the working muscles, at the muscles, we're about 70% saturated. So there is not as much oxygen there as there is at the lungs, which is nearly 100%. So what's happened to that 30%? Because it started in the alveoli nearly 100 and now it's down to 70. So where's that 30% gone? Well, it's gone into the muscle cell, of course. That's where it's disappeared. It cannot go anywhere else because the membranes are too thick. So it can only move when you're in a capillary, and those capillaries are only at the alveoli and at the working muscles, as far as we're concerned at the moment. So now let's have a look at what happens to the line when we start to exercise. So you can see that the line has moved to the right. It's a shift to the right hand side. That shift was recorded by somebody. They discovered it. They tested people when they were exercising what the saturations of oxygen were in their blood at the same partial pressures at 40 and at 100, and they got different readings. So now when we read from 40, which is at the working muscles, we're now looking at around 60% saturation. When we're at 100 at the alveoli, you can see that actually that was still nearly 100. So that hasn't really changed. So we're not interested in what happens at the alveoli because we've still got oxygen saturation of the red blood cells at the lungs because of the diffusion gradient. What we're interested in is why at the working muscles this line has caused a 10% decrease in red blood cell saturation. So there's an extra 10% disappeared somewhere. It's gone to the working muscles, of course it has, because we needed that extra 10%, because we were working out, because we're exercising. So what the oxygen dissociation curve shows is that when we exercise, the curve shifts to the right. The curve shifts to the right because there's a reduction in pH caused by carbon dioxide increase, caused by hydrogen increase in the blood, and also caused by an increase in temperature due to movement and energy production. So that shift to the right is caused by pH and temperature. That shift to the right then means that the body more readily gives up oxygen. And we know this because 10% more has disappeared into that muscle cell. So by the line moving shows that more oxygen is more readily dissociated from hemoglobin. I hope that makes sense.